Welcome, everybody. How are you doing? Okay, did we get through some of the complexity of how this course works? Okay, so today we have Group A here with us, and then on Tuesday you'll be in DSV and EIT. Okay? Administratively, we have a pre-survey that is due on the 28th, so before the next class. Many of you have already seen that it's up on campus, but if you haven't done it, go ahead and do it. That one's actually worth a point. Okay, it's not so much what you write; it's just if you do it. I mean, it'd be nice if you wrote what you think accurately. Okay, but please get that in. Any questions in terms of what's going on? So today, right? Hopefully we can have some interaction. We can talk a little bit, discuss some aspects of particle dynamics, some methods that we use for simulations, and also orbital mechanics. Okay? And then on Tuesday, you will have a lab, and it'll be due 30 minutes after the lab, but it's already up. So you could say, hey, this is a slow weekend. I'm just going to go ahead and do it on my, on a Friday night or something. And then you don't even have to show up on Tuesday if you so desire. Okay? Just make sure that you've got it done before 3 p.m. Before 4 p.m. on Tuesday. Does that make sense? Now, if you're in Group B, they'll have theirs due on Thursday at 4 p.m. Yes. Is it unfair? I don't know. Because you both have the post-lab exercise due that following Tuesday, right? So you have a little bit more time between when you do the lab, if you choose, if you desire, and when you have the post-lab exercise due, then Group B does. All right? Any questions on that? Yes?
Will the due dates for the assignments pop up for example?
I hope so. They should, right? They should already be there, right? So the lab one and the post-lab exercises have all been released this morning, okay? So if it's not there, let me know. And I think you got most of the group stuff worked out, all right? Thank you. It was an interesting experiment. I'm sorry some of you were randomly put where you didn't want to be, but we had to fit the constraints of the system. All right, well, let's get going then. Any questions? And I'm sorry, what was your name? Olivia. Okay, thanks, Olivia. All right, so today we're going to discuss a little bit about particles, how we approach them, how we think about them, and then we'll talk about how to essentially solve in time for their position, for their velocity in a gravitational field. Okay? And so after that, we'll use Euler Method to do that. And then we'll talk a little bit about convergence, and then talk about another method that is a little more complicated, but will get us to solutions more quickly, as you'll see, both in the lab and the homework. And then finally, we'll talk a little bit about orbital mechanics. Okay, so that's kind of the plan for today. So what should you take away from today? Well, hopefully, you'll either be reminded of Euler Method, or learn it, have some understanding for how it works. You'll have at least an appreciation for the velocity Verlet method, which is a little bit complicated. I wouldn't expect you to just oh yeah, that's real intuitive. You'll get to intuit more when you do the lab, because you'll be putting that into MATLAB. And then hopefully also get a little bit of insight in terms of the general idea of convergence, okay, and orbital mechanics. Okay, so how do we approach particle dynamic simulations? Well, for us, and we'll talk about different types of particle dynamics simulations, but for us, we're often concerned about gravity's effect on neighboring particles. Okay? We know that we are on this Earth, and that the Earth has a large mass, and we have small masses, and we feel attracted to the Earth. Okay. Now, with these kind of particles, what do you think? I guess I kind of said it already, but what would you be interested if you have a couple particles and they interact with each other? I mean, what do you want to know about them? What do you want to keep track of? Yes.
How far away they are from each other?
Sure. How far away they are, right? Because that will tell us what the force of attraction between the two would be. Yes. And your name is Matthew. Okay, Matthew. And we talked just briefly before the class. Yes. Right. So you want to know speed, and if I know the direction, then speed, that is velocity, right? So that's another thing, right? We might want to know acceleration as well. So we're going to go ahead and keep track of position. We're going to keep track of the velocity, and we're going to try to use acceleration to help us integrate up to those others, right? That's the point. And so if you look at some particle, you could see that it has maybe a position, okay? And position is often relative, right? But this is just a single particle. It might have a velocity, right? It might have some forces acting on it. Okay? There could be multiple particles that are neighboring it, so you have multiple gravitational forces acting on it. And it could have some acceleration. So, in the class, we focus on simulation. So there are often closed form simulation or closed form solutions to these types of problems. For example, if I say I have a particle that is, I don't know, a meter. How tall am I? Maybe a meter. I'm not that tall, right? But anyway, 5 feet plus above the ground, right? 1 to 2 meters above the ground, and I dropped it. How long does it take for it to fall in our Earth's gravity? Like, how do you do that? How do you calculate that? Right? So anyone? Physics, right? Yes? Okay, so kinematics, describes motion. Typically, we think of kinetics, right, as describing the combination of the motion with the forces. Right? So in this case, I've got gravity acting on the object, so it's more of a kinetics problem, I'll argue. All right? But I just want the closed form solution. Yeah.
Like how long?
Yeah, how would you calculate? What is the equation that you use to calculate how long it will take for this ball to fall from here to the ground?
2 times the height over e square root of square root of that.
Yeah, you got it, right? So like d, I just think of it as the distance equals 1/2 gt squared, right? Right? That's the equation you remember, right? If it's got no initial velocity, right? So we know that we can describe that, okay, displacement with a closed form solution. Right? And that's, so, at this point, you've got a lot of closed form solutions that you've been exposed to over time, right? What we're going to do, right, is we're going to take these interactive forces and essentially not give you the closed form solution, but tell you what's happening as we go through time, right? So, another thing is, if you want to know the position, you can use a closed form solution, right? So if you know that you're like, okay, how much time has elapsed if I've gone down a foot, right, from my initial? I can calculate all those things, right, using my set of closed form solutions that you've had in your physics class. Okay? And in simulations, there are kind of 4 steps. One, we want to establish the basic physics. Okay, so in this case, forces are going to be important, right? And it's going to be gravity, right? And we have this universal gravitational constant, the big G, all right? And we're not really going to, well, we are going to use that, okay? But typically when we're on the Earth, we don't think about it so much, right? We just think 9.8 meters per second squared. We have to start the simulation. That seems pretty straight, Yes, you have to start. We have to establish and respect boundary conditions, right? So, like, that's not just a personal thing, right? Like, maybe you're familiar with, like, not just physical boundary conditions, but, like, my time and my space, like Brene Brown type stuff, or whatever. I don't know, maybe you're familiar with some of that. Establish your boundaries and then stick to them, okay? And then we iterate. We run the simulation through a series of time steps. And so that's really what we're going to do a bunch of times this semester, okay? We're going to follow these steps. In this case, the discretization is, well, you tell me. I have it, it'll show up here in a second, but what do you think we mean by discretization? What are we discretizing, right? So we know that we live in like the analog world, right? And yeah, computers are discrete. Yes. Okay. Yeah. Will here. What's your name again? I can't remember your name. Will. Okay. Yes. Will.
Discretizing time.
Yeah. So discretizing time would be a good thing to discretize here. Yes. And it depends a little bit on the simulation you run. Okay. So we've discretized time. What else might we discretize in a simulation? Yeah. Space. Okay. Right, so that's pretty much what you're down to, right? You're figuring out how you're going to discretize time and how you're going to discretize space. Yes, Olivia. Okay, so it means, and we'll get to this, all right? But let's do this, all right? It means that we're breaking the problem into discrete units. Okay, so some of you have heard of finite element analysis, which we are going to cover in this class, or finite volume analysis, which we're going to cover in this class. All right, or finite time difference. Right. So finite. Right. That word finite is in all of those. So we have to take whatever we've got and we got to break it up into pieces. So we could think, all right, I've got particle A here and particle B here, and I'm going to make a big grid. Right. Make a 2D Cartesian coordinate grid, and I could break it up that way if I wanted to break up space. And then I've got to think, how many time steps do I want to take to model the particle from going from this spot to this spot? So my total time of my simulation might be 10 seconds, but I'm going to try to break it into chunks of 1 second. Or sub-second increments to get from here to here. Okay. Now, in this problem, well, the problem. What is this? This problem being the particle dynamics simulations. We are going to discretize time. We're going to think about time steps, and we're going to essentially say space is continuous. Right. So I can essentially, in a given time step, okay, I can say, I could go like half a meter, I could go 1 meter, I could go 0.25 meters, I could go 0.75 meters, I could go 0.76 meters. It doesn't really matter, okay? I'm not confined to being on some type of grid in space, okay? I am confined, though, to be at certain time steps as I run my simulation, okay? And so as you can see, right, you're going to have a position at, let's say, some time, all right, t, all right, and then you're going to try to figure out where you are in position at the next time step. So maybe t is equal to 0, and your time step is 0.1 seconds. So then the t plus 1 would be 0.1 second later, right? And to do that, you need to know what your velocity is at your current time step, right? And then you multiply velocity times time, and that gets you to the next position. Right? Does that make sense? And if you're thinking about how the velocity, though, is changing at the next, from this 0 to my 0.1 time second, then I need to know what the acceleration is at time 0, right? And multiply that by time so I can figure out what the new velocity will be when I get to the next time step. Okay. This is the most kind of essential way of breaking up the problem and calculating velocities and the next time step and accelerations in the next time step. Essentially, these two methods that we're going to discuss today, Euler and Verlet, they approach how you figure out the next velocity or the next acceleration a little bit differently. And so there are tricks. But based on what we know in our physics, right, distance is equal to velocity times time. Velocity, or the next velocity is equal to acceleration times time, right? So that's from our kind of our Newtonian background. So the acceleration in the types of problems that we're going to be looking at, right? So you can kind of see you got to go from here, acceleration times time, right? Then you can kind of figure out what's happening with velocity. And then if you know what's happening with velocity, then you can figure out what's happening in position, right? So the acceleration is going to be dictated by, the force divided by the mass. And if we want to think about the position, all right, so kinematics, all right, again, so that's describing the position, and kinetics will be this kind of force interaction with the system to describe what's happening there. Okay. We can figure out the position at any given time, okay, by essentially summing up all these different positions that we've been accumulating and that have been multiplied at time steps. Okay. And we can look at the velocities, all right, by looking at the initial velocity, right, where it is, and then summing up, again, these velocities at all these different time steps. Okay. So if we now talk about and revisit, potential schemes, all right, we can say, what are we discretizing for particle dynamics? Well, we're discretizing time. And what is continuous? Space, all right? So let's go back to that example of a ball falling to the ground. Here we have our particle, we have a direction z, and we can say that there's an analytical solution and there are simulation methods. Okay? And some of those are the ways we can approach them. So there's Euler, there's maybe a modified Euler, there's Verlet, there's velocity Verlet. There are different types of, these down here, these are the simulations. Okay. And I guess just as a moment, but we kind of talked about this, right, in the last meeting. But why would I ever simulate anything? Like, why don't they just use analytical solutions? Yes.
Sometimes the analytical solution is too difficult to do.
Okay, right. So you can't come up with an analytical solution, right? That's a good reason to use simulation. Can you think of? Yes, Paul.
If your conditions are changing based on different time.
Right. Yeah. So a closed form solution for the weather, right? That's not going to happen. I mean, maybe there is some big equation out there that can account for every little thing, right? But we don't have it. So as conditions are changing, right, you update your predictions. Yeah. So those are pretty much good reasons. Okay. So analytical solution for an object falling. The initial position is 0. The initial velocity is 0. Okay. The acceleration is constant. Okay. It's going to stay that way for the time of our problem. And for a 1D problem, which is kind of what we're looking at here, we can say that this position r is only described by one parameter, the z, okay? So how far away we are from the original position. And when we do orbital mechanics, right, that's going to be kind of like a 3D type of problem. We're actually going to, it essentially becomes just a 2D problem the way we do it, because we're going to think of a plane, we're going to think of objects orbiting around the Earth, satellites. And so it's good to realize that that's a vector, okay, that describes that position. You know, center of Earth, position of satellite, 2D, I have two coordinates that are changing as I run through my simulation. Here we just have one. And we're focusing on the closed form solution. So the acceleration, we could say, oh, x is going to be z double dot, t, right? That's equal to g. And we can say the velocity is z dot, okay? And we know that the velocity will then be gt, and we know that the position will then be 1/2 gt squared. Okay. And you're like, why did you just waste our time with this? Well, the reason we're going to waste our time with this in a few minutes is that we want to compare our simulation, when we can, to the closed form solution. Right? So this is the baby step, right? So you know, I make my nice little computer code program, and then I want to see, okay, how well does the Euler method compare to what I can get from Newtonian mechanics? And I expect that I won't get it exactly right. Okay? There's going to be a difference. Why? Because I've discretized things, right? I can only be at some time as I'm running through this simulation. And you'll see that the length of the time, or the size of the time steps that we choose, dictates the amount of error that we're going to have between the closed form solution and the simulation. Okay, so here are the 4 steps again, and here's just a little bit more background on it. So yes, we had to establish the physics and the discretization. So we just said, okay, that's the closed form solution, but we also said, okay, I know that I'm discretizing time and space is continuous. Okay, now we had to think about number 2, initialize the simulation. So we want to know the initial position, and we want to know the initial velocity. And it's important that we keep track of them. Okay, so there are kind of different ways of doing this, but we're going to be using MATLAB, right? So you can think probably vectors, okay, that we're going to index if we want to keep track of the information. And sometimes we only want to record the information like every 10 time steps. So imagine you break a problem up into itty little bitty pieces of time. Okay? Like you want to do like 1,000,000 time steps. Okay? You don't really want, like, for your intents and purposes, when you plot it, you don't want to plot the position at every one of those 1,000,000 time steps. Okay? So you can use a modulo function, and if any of you did like the MATLAB reveal, right, you might have got a little bit thing here, right? But if I have something, let's say I want to keep every 10 steps, right? I could take, all right, I'm going to do 100 time steps, 100 modulo 10, right? Would be 10 different things I'm going to keep track of, right? The clock is the most common example of modulo, right? You know that if I add, I don't know, what time is it? It's like 2 something, right? So if I add 14 hours to our time right now, it's going to put us in the next day, right? And it's beyond the 24, right? 26, if we're on a 24-hour time, right? Or if you're on modulo 12, so you modulo 24 or modulo 12, right? But either way, you know that 14 hours from now, if it's 2 o'clock, is that would be 26. That puts us up like 2 a.m. or something. Okay, so actually no 4 a.m. right? So that's kind of how modulos work, right? So you're going to use modulos to keep track of positions and velocities, accelerations potentially at different set times, but your simulation can be running much faster. Why do you do this from another practical perspective besides like I don't really care about every one of those 1,000,000 time steps? I do it because of speed, right? It takes time to write values to and from memory. It takes memory, and as that memory grows, right? So you also want to potentially run those little time steps really, really fast in loops and only keep a few of them and only burn a little bit more time, 1 every 100 or so. Often so will acceleration be counted as an initial condition? Well, maybe not. In the closed form problem, okay, we said that acceleration was the same throughout the entire problem, okay, but maybe you say I just want it to be 0 initially, right? So you have kind of a choice. With the second, establishing boundaries, okay, space, like orbital mechanics, right? The final frontier, yes, right? Star Trek, okay. Besides hitting another planet, okay, which we don't really take into account when we do our orbital mechanics stuff, right? So that's a hint. We don't really have any boundaries, so that's kind of nice, right? Even if I'm talking about my ball hitting the ground here, or the time for that to happen, like, right now I don't want to think about what happens when it hits the ground. Next time we meet, we'll talk about what happens when it hits the ground. We'll talk about balancing. Okay? But for now, there are no boundaries. And when we think about the steps in the simulation, we already discussed a little bit about how that works. Hopefully that's helpful. If what I'm saying sounds like, oh, why is he talking about this? Some of it is because I'm just rambling. But some of it is actually because when you do the code, you're going to need to keep these things in mind, like the modulo, the container that you use to kind of store information every now and then. You're going to want to, you'll see as you do the simulations that stuff is important. So we're only going to cover Euler and the Verlet method today. Okay. So what are, let's just think for, a few minutes here and maybe take a little bit of a breather, but what are kind of possible forces that might be applied to a particle, and how would we treat a situation where there are multiple forces applied to the same particle? So open. What do you all think? Yeah, sure, Federico.
Normal gravitational body forces. Like
Okay, so body forces, that's good. So that's, to be honest, for particle physics, that's pretty much synonymous with saying the forces, right? Because everything except, well, if it bumps, for now, right? Unless, okay, if you hit a wall and you bounce off, yeah, okay, something interesting is going to happen. And so, that's a reaction. If the particles bounce against each other, you could argue, okay, well, that's a little bit different. We're actually going to treat a lot of these things as body forces, or we're just going to do some reflections, all right? So, like, the velocity going in is equal to the velocity going out, right? But pretty much, all right, right now, body force is synonymous with the force that we're thinking of. Okay? So what are some body forces? Yes? Okay, so electric. So there could, yeah, so you want to be a little more specific. So when you say electric? Yeah, so electrostatics, right? Okay. So in the electromagnetic realm, you're going to have your electrostatic forces. All right, you said like Coulomb interactions. And then you also have, yes?
gravity.
Okay, so gravity, yes. All right, so gravity. That's an important one. We talked a little bit about this. Going back to this, I was just wanting someone to say electric. Yeah, magnetic, right? So that's like Lorentz forces, right? And it could be from current in a wire, it could be from a permanent magnet, yes. Okay, so you could have, yeah, so that would be like a contact force, sure. All right, like we're kind of ignoring them for now, but you could have contact forces, right? But hopefully not for particle. For gravitational. Okay. Anything else? Yeah. Okay, Federico. Yeah.
Not sure if this is strong and weak nuclear forces.
Sure. So you have weak forces, which I don't really understand, but have to do with like decay of particles, and then you have strong forces, which are like kind of what keep everything together. I mean, that's like kind of a layman's, an engineer's approach to describing these. Okay. And then maybe the other thing is, how do we handle, what is the word that we use when we have multiple forces acting on an object, and we want to know the net force? Yeah, superposition, right? Who said that? Yeah, okay, what's your name again? Huh? Bobby, okay, not again, I guess it's the first time. Okay, good to meet you, Bobby. Yeah, so you could have superposition, right? Okay. What's another for the fluid mechanics people? Hold on. All right, hold on. The fluid mechanics people. Hydrostatics. What kind of force could you have on a particle? Yes? Huh? Pressure. Okay, so pressure, yes. So we could have David Bowie and Eddie Mercury here in town. So we have pressure. And in hydrostatics, that usually leads to what we call, yes, based on density, huh? Yeah, buoyancy, right? So yeah, so usually, right, we then think about buoyancy. We come up with this kind of potential field, right, rho GH, and that describes the pressure actually, right? But then we think about the deltas of the density, right, times the GH, and that gives us the buoyancy. Okay. So, no, that's not right. If you use the buoyancies, yeah. You need to know the volumes, the densities, and then you can figure out the forces. Okay, good. So, what are some physical situations that can be represented by particle dynamics? Yes, your name?
Spencer.
Spencer, yes.
Orbits.
Orbits. Okay, good. Yes, we're going to do orbital mechanics, so good. Anything else? Yes, Olivia.
Projectiles?
Yeah, so projectiles. Okay. Yes?
Collisions.
Collisions, okay, yeah. So particle physics and non-particle interactions. Yeah, what's your name? Meridian? Okay, great. Any others? Any other ideas? Yes. Charges, yeah, right. So charges, how they interact with each other, and usually they have to have some mass for us to, be excited about it. And your name was Emily? Okay, all right. I'm not. Some of you I will know by the end of the semester. Some of you, for better or worse, I already know. Okay, all right. But we'll get there. We'll get there. Okay. Other things? Yeah, sure, Federico.
Oscillations or yeah.
So yeah, so
Vibrations.
huh?
Vibrations.
So okay, so let's talk about So yes, so you could have. Okay, so let's clarify. So vibrations could be spring networks. Okay, so that'd be like particles in like vibratory networks, right? That could be gas molecules, and we'll talk about that a little bit. All right. Whoops. And going back to orbits, what kinds of things are we thinking about with orbits? Because I mean, you said orbits, but what kind of particles are in orbit? Yes.
Planetary systems.
Yeah.
Hypothesis.
Yeah, so planetary systems, galaxies, right? All these different type of objects in our universe. Okay. Anything else anyone wants to add? That's pretty good. That's pretty good. So what we're establishing today is a framework that could be used to describe a lot of these different systems. Okay. We won't talk too much about, how things vibrate with each other, but we will talk about this a little bit in a couple of weeks. All right. Let's get to the Euler method. So there are ways of integrating where we use just what we said before. We figure out what the velocity might be and multiply it by the time to get the next position. There's the way to get the velocity by multiplying the acceleration by time step plus the current velocity to get the next velocity. Okay, and there are also approaches that have to do with, how do you say, tricks, essentially solving for the next time step by also using the next time step. Okay, so the kind of the basic Euler method is what you call explicit. Right, explicit, and so there are kind of two classes of iterating methods. One is called explicit, the other is called implicit. Okay, those are the two classes. So Euler method is explicit, where it says, I am just going to use what I know in my current time step to figure out what's going to happen in the next time step. And then the implicit formulations, which we we won't really talk about much in this class. But the implicit ones are, I know something about what's going on in my current time step, and I want to figure out what's going on in my next time step, and I'm going to use another piece of information that tells me a little bit about it essentially tells me what's happening in the future already a little bit, and then I make the jump to the next time step. Okay? So the good thing about implicit is that it can be fast. The bad thing about implicit is it can be complex, and there may not be, or there will be non-trivial implicit characteristics, because you have to know something about what's happening already in the next time step. Okay, this is kind of layman's term, but essentially what you would see is, if we're using, what are we using? Which variable are we using here? We're using y. So essentially we're saying y of I plus 1. So I know my y sub I, where I am right now, my state right now. My y of I plus 1. All right? What you then write is that your y of I plus 1, or y of I plus 1, is equal to some function of yi plus some function of y of I plus 1. Okay? So you have to know something about the future for the implicit. Here, the Euler, like we said, is explicit. And this problem, again, is kind of trivial, but we're going to go through the accounting process. What do I mean by the accounting process? I mean that we've got to look at the accelerations, look at the positions, and look at the velocities at the current time step, and then figure out how that affects the next time step. Okay, so in this case, all right, if you have this object, okay, we can say mz double dot is equal to mg. All right, remember that? Okay, that's just Newton coming in here, third law, and we know that the acceleration is equal to g. All right, and in this vector that we have, okay, we can keep track of, and it may be a little bit hard to see, but this is y of I, y sub I plus 1, and this is y prime I plus 1. Okay, so that means that I'm thinking about z, right? Because I'm using this parameter z. I'm thinking of z in the next time step, and I'm thinking of z dot, right, or the velocity or speed in the next time step. Okay. And on this side, what I'm saying is that this next time step is going to be dependent on what's happening in the current time step with both the position and the velocity. And in order to figure out, okay, velocity in the current time step, I need to know the time step. In this case, they're using h as the time step times the acceleration, right? This is exactly what we did a few minutes ago, right? And this is now just formalizing it in what we call the Euler method. So h is the time step, okay, and z double dot I is going to be our g. So we're only going to use, all right, the z and the z dot here, and the acceleration will come into the calculation, though, right, of the z dot. So this is where acceleration comes in, okay, right here. Now, let's make a little table. We have our time step, we have position, our current velocity, our current acceleration. And we are going to be trying to figure out what our next position, our next velocity will be, given a time step delta t. Okay? All right, you see where this is going, right? So the comparison we can also add here. This is ground truth. All right, we already said that's the analytical expression that we want to replicate with Euler's method. So here we go. Time step 0, our initial condition. Well, the position is 0, the velocity is 0, or the speed is 0, and we know the acceleration is g. All right. Let's use as our time step 1, okay, to keep it simple. So now, help me out. What should z dot sub I plus 1 be? Anyway. Yes. Okay, which is G. Good. Your name again? Nick. All right. So it's G, right? What is the zi plus 1? Well, the time step is 1. This velocity is 0. Okay. And it was 0, so then the z of I plus 1 is going to be 0. Okay. Everyone see how this is working? Okay. So let's move. I guess we can also say, okay, so what is, this predicts also 0. Okay. So, all right. We haven't gone anywhere, and we agree with our ground truth. That's great. Okay. Now, what happens next? Well, we start looking at populating what we have at I, right? So what do we take? We take our z of I plus 1 and we move it over here. We take our z dot I plus 1, we move it over here. And z double dot I has not changed, that's still g. Okay, everyone cool with this? Now, what is z of I plus 1? And what is, or z dot of I plus 1, maybe we want to calculate that first. Or maybe we don't. We don't really, we have a zi dot, so we can calculate either one. All right? What is z of I plus 1, for example? Here. Yes?
Is it G?
Yeah. Right? How did you calculate that out?
Because positions G I.
Uh-huh.
Because our velocity is also G, so it's going to move.
Yeah. Right. Okay. So what you're saying is that z of I plus 1 over here, right, is going to be equal to this top row, all right, and it's the zi, which was 0, plus 1 times the g, right? And that's going to be what goes there. What comes over here? Well, the z dot I plus 1 is going to be equal to this row, and z dot I, right, we had over here is g, 1 is delta t, z double dot I is g, so it's just 2g. Okay? Now, what is the prediction here? What does the ground truth say after 1 second? Yeah. Right. So you're like, this is garbage. I'm off by a factor of 4 already. Yeah, maybe. Huh?
Factor of 2.
Well, oh, sorry. Yeah, I'm off by, yes, right. Not factor 4, factor 2, right? Yeah, so like, why am I doing this? All right? Well, to show that it does do a good job, kind of, and it's also useful to compare against ground truth. So we can keep doing this exercise, and we can keep filling things out in this table at these different time steps, okay? And we see that the error, right, continues to be present. Okay, so what do you think you could do to decrease the error? I think you already know, right? Hold on. Yeah, what were we gonna say? Yeah. Yeah. So you can reduce the time step. If we make use of smaller time steps, right? Then we can not kind of overstep too much with the given amount of velocity that we've calculated when we're doing positions, or the next velocity when we're given the current velocity, right? So as we make that time step smaller, we can do this. And as we mentioned earlier, this Euler method is explicit. In other words, it just uses what we had in our current time step to predict what's going to happen in the next time step. And this is called forward Euler method. Okay, now, how should we go about implementing this? Well, the fast answer is code. All right. Okay, that's kind of the fast answer. All right. The the more involved answer is we need to keep track of a few different things. All right. So you see in our simulation, how many time steps are we doing? We're doing essentially 1, 2, 3. We're gonna go through 3 time steps, or and it depends a little bit on how you index your matrices. All right. MATLAB is typically 1 index, right? Meaning if I have an array or a matrix, I say I want the element in the first position or in position 1, 1, right? That gives me, in the matrix, that gives me the upper left corner. Python, typically, if you're using NumPy, it's 0 index. Okay? So you have, you're like, that, the first position is going to be 0, 0. Okay? Just something to keep in mind. I mean, these kinds of things always drive me nuts. And you guys, in mechanics, it was, okay, is it up, down, positive or negative, right? That's the kind of thing that drives me nuts there. Sometimes here it's like, how many fence posts do you have, right? Versus how many slats do you have, okay, as you go between the posts, right? It's these kinds of things. They just, it's either one or the other. It's like you got a 50% chance of getting it right, and I'll get it wrong, okay? But here we go. We have 3 iterations. We have acceleration, 9.8. Our initial position is 0. Our initial velocity is 0. And gravity throughout the problem is g. Okay? We have containers where we are going to start with our z's, all right, our positions. We're going to have our z dots, all right, and we'll have t. Of course, z double dot is not changing in this problem. So that's kind of not that interesting. Okay, so, or it's, I don't have to make a container for that. And yes, and MATLAB will tell me, yes, you don't even need these brackets. Okay, and MATLAB will also often tell you that it's not efficient to create an array and keep adding elements to that array. Okay, instead, it's more efficient for the computer if you tell it how many are in the array, and then you just populate that array. Right? You could do that. I'm doing it not that way. Okay? So I'm doing it the inefficient way. Because you see what happens here? We're saying, look, the container, and in this case, the container is keeping every single, all 3 iterations. All right? It's not like, we're not breaking the bank in terms of amount of memory and time that we're needing for this. Okay? So we're going to go in a for loop, and we're going to go from 1 to the number of iterations that we have, the maximum, that was 3. And then we're going to do what? We're going to calculate our new z position using the Euler method. We're going to calculate our new velocity using the Euler method. Okay? And then we'll say, oh, you know, the next time step where you are is going to be the current time plus the dt. And we're also going to track, because we have the luxury of having a closed form solution, we'll calculate the error right there and there, right? The closed form solution is 1/2 gt squared. Okay. And if we want, we can make a matrix with this whole thing. All right, this is the overall matrix, and we can spit that out. All right, so when we run this, it's busy. It's thinking. I'm surprised it's thinking that long. Okay, well, it had to think a little bit. All right, and this is the overall matrix. So what is this? Okay, so this is, right, our iteration. Now notice we did 3 iterations and we started with 1. Previously we did 3 iterations, or I showed 3 iterations on the slide, but we started with 0, right? Again, just, could I have called it 0? Sure, okay? Is it, am I calling the, you know, the first next one 1 in this case? Yeah, all right? Is that confusing? Maybe, all right? The next one is the z's. So these are the positions. The next column is the z dots. The next column is just the acceleration, which is unchanging, okay? And the next column is going to be the ground. This is the ground truth. And then this one is the error. Okay, does that make sense? So when we go back to here, okay, what you see is that we can write it out kind of nicely, like you see here, and we can put these 3, you know, these different columns through these 3 iterations here. I can say, oh, really, that's just the 0, 1, 2, 3. That's what we're calling I, and off we're going. So in this case, the error, right, is the difference between the ground truth and what I predicted. What do you notice about the error? What? Okay, that just blew my mind. Anyone? I mean, maybe it's obvious, right? It's increasing. Okay? It's increasing. Now, in terms of a percentage, so you know, you could argue that it's maybe decreasing. Like it went from 0 to essentially 100%, right? To like about half, to maybe a third, right? So like percentage-wise, it might be decreasing, but in terms of the, you know, actual quantity, it's increasing. Yeah, and that's just pointing out that these are the actual, we calculated this out already, right? And that's the error, okay? Now, we're going to think about this error a little bit and think about convergence. And some of you already said, oh, well, all I got to do is reduce the factor, or the time step, okay, by a given factor, okay? So I guess there are multiple ways to look at this, all right? One is, okay, how many time steps do you want to use? And the other is, how big is your time step, right? This is going to be confusing to some people later on in the class, but hopefully I'll say it and we dare. If I increase the number of iterations, but I keep the amount of time, total time I'm running for the simulation, the time step goes down, okay? If I increase the time step, the total number of iterations that I have goes down, okay? Or that's how you draw, that's how you put opposite problem, okay? So if I decrease the time step, the number of iterations goes up. If I decrease the number of iterations, the time step goes up. What is the perfect number of iterations for the perfect number of time steps, or the perfect size of time steps? What do you all think? You haven't. What's your name?
Max.
Max. Okay, Max, what do you think?
The infinity.
Whoa, infinity, infinity, infinity. I love that. Okay. Why are you saying that?
Because it makes the smallest possible interval. Like if you have like infinite steps, the interval between.
Okay. Right. So if I use an infinite number of iterations, then I could have really high accuracy, right? Now let's put our practical engineering heads on. If I need a simulation that has infinite number of steps in it, will I ever get done with the simulation? No, right? So perfect, let me say that is one way of thinking about having 100% accuracy. Okay? From an engineering perspective, and that's the fun thing about some of these numerical methods, is that they're actually very practical. They're very much engineering to get you to a solution. So how would you engineer this problem? Okay, go ahead, Federico.
You would see there could be a steady state, like steady state result, and you try to run it so you get to that steady state tomorrow.
Okay, this is very, very good. All right, so what you're saying is, and it's actually one of the ways we determine convergence. Okay, you could start with a large time step and keep reducing that time step until your simulation is unnoticeably different, at least for your intents and purposes, right? So, for example, if I start with a large time step and I predict that I'm going to end up, at the end of my overall time of simulation, I'm going to end up 2 meters away. But I have a very large time step. Let's say I start with a time step of 1 second. And I predict that I get to 2 meters with that 1 second. Then I half the time step. All right? I go to 0.5 seconds. Now I get to 1.5 meters at the end of the simulation. Then I half it again. I go to 0.25 seconds, and I get to 1.25. Right? And I half it again, I get to 1.8. I get to 1.125, right? Eventually, I start seeing that I am getting closer and closer to this number, whatever that number is. I think that's what Federico is meaning by steady state. Okay, you get to whatever that number. You're getting closer and closer to a number. That means you're kind of converging on that number, right? And you might converge. You might go a little bit under one time. You might go a little bit over, depending on the numerical method you're using. Right? But you eventually get to that number. You can say, I converge within 1% of my previous time step. Okay? Or I converge within 0.1%. That's good enough for me. I'm done. No more reduction of time steps size, because if I reduce the time step size, right, I gotta run more and more simulations. So you essentially what you try to do is you reduce the time step until you get something that is accurate enough for your intents and purposes. That is, quote, the perfect balance between the number of iterations you use and the size of time steps. Okay, but they're flipped. Yes?
The accuracy is determined by like taking the error.
Okay, good. Okay. In this case that we're talking about, this exact problem, I have 2 ways to look at error. Okay? Actually, kind of one that makes sense, because I have a closed form solution. So another way to determine convergence is to say, I know what the ground truth is, or in geosynchronous orbit, which we'll talk about, I know that after 1 day, I'm going to be exactly in the same spot again. And the next day, I'm going to be exactly in the same spot again. All right? And I'm going to say, oh, my simulation doesn't say I'm in the same spot again. I'm off. These are ground truths. Okay? This is a ground truth. So I can also compare to the ground truth and keep going in the reducing of the time step until I've got essentially close enough to the ground truth that I'm satisfied. Numerically, will I ever hit the ground truth? Well, maybe. Okay, maybe. but often it'll just be some minuscule amount off once I reduce the time step enough, right? Does that make sense? Okay. So this is how we talk, and I'll write a few notes on it in a minute, hopefully. Go, we gotta go. Okay, all right. I'm having so much fun with you, but we're not getting through the material. All right. Okay. So here are a few things. Okay, the error, right, versus the number of iterations. This is confusing often. Okay. The error is going down. You see that as the number of iterations goes up. Right? Another way to look at these, okay? Okay, so one is, okay, if I use the same time step and then I look at the final time, that's not what I cared about too much. Okay? Where's the one I want? Okay. No. Okay, I'll show it over here because this is going to be more relevant to what you have to do. Okay, so the number of iterations goes up. Okay. Okay. This is what you're going to care about. Okay. And this is the point I was trying to make. You see, there are two ways to plot the same stinking thing. All right. You see that these graphs are mirror images of each other. Okay. On so it's a little confusing. On the x-axis, all right, on the left side, that's time step in seconds. That's not number of time steps. Okay. So what that's saying is that on the left side, I have a very small time step. Well, maybe not really small, but it's 1/10 of a second in this case. Okay. And then this is a logarithmic plot. So you have 10, 10, or 1/10, 1, 10, 100, 1,000. Okay? So as the time step is, and you know that these slides are available, right? Just so you know, right? Don't sweat. But sweat, I know, I understand you get things out of your memory. So as the time step is small, the error is small. So you would have, well, you could have done either thing. For the purpose of creating this graph, you could have started with a small time step. From an engineering practical perspective, hopefully you started with a large time step and you moved down. All right. But often in these simulations that you're going to be doing, you're gonna just start from the small time step and you're going to work your way up. Okay. And then here it's the opposite, right? Here we have a lot of number of steps, and then as you increase the number of steps, right, your error goes down. Okay? This is usually how I like to think of convergence. All right? And some of the softwares also think of convergence this way, is that you reach the steady state as the number of steps you use increases. But it can go the other way too, right? It can be, the size of the time, or it could be 1 over the time steps, whatever. But you're going to see, especially when we do ANSYS and these other simulation packages, they are going to show you more or less how you're doing in terms of convergence. Okay? And so they're going to help you understand, okay, yeah, I've at least converged on the solution. Now that solution could be absolute garbage, okay, it turns out. Okay? Because if you don't know the ground truth, you don't know what's going on. That's another reason why we do baby steps. Okay? We start with something that we do know the answer to, and then we can go about figuring that out. Okay. Now, so I just want to say a couple things about convergence. All right. So convergence. Because this is important, and I think I didn't emphasize it well enough, and then when I started seeing people's reports and things, well, anyway, just talking to people, I realized that convergence, I didn't emphasize it enough last spring. There are essentially two ways to show convergence. Okay? And you know, the first way is show the error relative to ground truth decreases with the number of steps or iterations or reduced step size. Now, remember, discretization right now is only time. These steps don't just refer to time. They can also refer to space, right? So what happens is you also need to converge if you're doing a finite element or finite difference. You're doing these different types of techniques. You also might need to converge by discretizing your space into more small chunks. Okay? And then the other way to converge, okay, is to show the difference simulations with larger steps or decreased or lower, we'll say lower, larger steps or lower number of iterations is decreasing. Okay? So you may not know what the ground truth is, but at least you know that you're getting closer to something as you're using more power, as you're doing more calculations. Okay. So that's how we think about convergence. Okay, those two ways. And that, if you remember that from this session, that will help you through the rest of the class. Because you're going to want to make sure that your solutions make sense, and you also don't really want to be sitting in front of your computer for longer than you have to be. Okay? And to put things in perspective, these simulations that you're running in this lab, you should only be running them for a few minutes at max. All right? This is not the time to sit in front of your computer for an hour, okay, for one simulation, or one set of simulations. Because you're going to show convergence. You're going to run lots of simulations. You're going to run it from a large time step to a small time step, or a small time step to a large time step, whatever. You're going to run it over these different ranges, and you just don't be crazy about making really small time steps. Okay? Now, the velocity Verlet integration method. Okay? There are 4 steps, and the first step is to calculate v. The second step is to calculate x. Okay? So we're calculating what's called the half velocity. So it's halfway to the next time step. Then we update the position. Okay? And then using that half time step, or using that half velocity, then we have to derive the acceleration at the next time step using the position, and that is using a potential field. And then we calculate the velocity at the next time step. Okay? That's the basic idea. All right? Now, you're asking the only thing that you probably is like really confusing, or maybe a little bit confusing, is what do we mean by calculating the acceleration at the next time step from the potential field? Well, we already have an idea that we're existing in some kind of potential field, okay, as we sit here on our planet. And very briefly, the potential field, all right, for gravity can be described by this minus g mn over r. And you're like, wait, that doesn't make sense, because force had that r squared in the denominator, right? So what you do is you had to take the gradient or the negative gradient of the potential, okay? And in Cartesian coordinates, this is what it looks like. And then you can calculate the force, right, that's acting on the object. Okay? So you're not going to, in your MATLABian world, right, you're not going to say, oh, I want to calculate the gradient of this. No, you're going to have this expression for force, a forcing vector, and you're going to divide by the mass of your object, right? Force divided by mass is going to give you an acceleration. And so that's what you plug into your Verlet integration method. Okay. So, just putting that out there. The orbital mechanics part of this, okay, you're going to be looking at a satellite that has a 24-hour orbit, so it ends up in the same place every day. It's got an initial velocity and it has an initial position above the Earth. Okay? And you're going to figure out a bunch of different things about it. First, you're just going to figure out how to simulate it using the Verlet integration method, which I will tell you how to do it. Just follow the video. Then you're going to need to use the Euler method, which we just described, to calculate the trajectory of the satellite. Okay? And then you're going to compare the two, and that will be your post-lab exercise. Okay? That's kind of what we're talking about. Any questions? All right, and just so you see, the orbits will look elliptical, all right, and anything. But any questions on what we've discussed? Okay. It's a lot. It's a lot. But you've done numerical methods before, right? Some of you have been exposed to introduction to computing, right? And you've done this, right? Yeah. Okay. Good. All right. Have a good one. See you in a week. Oh no! Oh no! Don't leave! Don't leave! Don't leave! Don't leave! Oh no! Shoot! I gotta do attendance. All right, there you go. Sorry for delaying that. This is the blue one. You want the blue one?
Can we get, does it matter if you can read the text on the screen because I can't?
It's okay. It's okay. Just get the thing in there.
You can see the words, like, you know, all these.
It's okay. You can see it's blue, right? Yeah. All right. See you in a week.
No lighting. Turn off the lights.
Turn off the lights.